Hello, am I audible?
Yes,
Hi,
ma'am.
yes.
Yes.
So we'll start now. Session screen test. So let's wait for 5 minutes because very listening people. It's already late for it. So in today's session, we will discuss, first we discuss some specific functions. So namely the modulus function and the greatest integer and least integer function, which I think you guys know by floor function and ceiling function. We try to observe these two functions. What are the mathematical expression for these two functions? And what are the graph of these functions? And then we recall what do we understand by limit of a function. Then using that, we'll define continuity and then jump to the differentiability part of a function. And there we spend some time over differentiability of a function, what is the derivative of function, tangent of the function, some basic rules. And at the end of the lecture, we try to cover up, we'll try cover the linear approximation of a function. So that's the plan. So let's wait for 5 more minutes. In between, if you guys have any doubt, you can ask.
Ma'am, I have a general question. The week 9 graded assignment deadline was 27th of this month.
Okay.
The quiz 2 is December 1. We are generally took the quiz 1 4-week content for quiz 1. After that, we chose the week 5. Why we?
Yeah, but actually this term started a little late. So I think for covering it into the 3-month window, that's why this thing is happening. So, and there is one Shastra and boot camp also happening in the campus. So I think by that effect and other constraints, so that's why we have to cover week 9 before the quiz. But the syllabus for quiz 2 will be up to 8 week only.
Oh.
9th week won't be in the week 2.
Ma'am, why the semester is on 22? It should be 29. Because the week 9 and 10 is very much close to the quiz 1.
Quiz 2, right?
Quiz 2.
Yeah. So this time
they
actually
should
discuss.
extend the 9 and 10, and then they should extend the end term date, because it within the December 29 also.
So end term is December 29, no?
No, 22.
22. Okay.
But if they give us date extension, then it will be scheduled on 29. But there is no, I don't think there is any chance of rescheduling the end
Yeah,
term.
so actually in this term, I mean, there are so many things happen. So boot camp happen and Shastra and all those things. So because of, and there are so many festivals also. So I don't know why they put like that, but those are the dates. So this term is actually a little shorter than the other 2 terms. But what can we say? So these are the date decided by the other superior members of the team. But if you have any, you are getting sufficient time for solving the questions and going through the content, except week 7, obviously.
No, not sufficient time.
Okay, it's not sufficient. I mean, for every week, going through every week, you have 7 days or 6 days.
देखिए मैं हिंदी में बोलता हूँ. क्वेश्चन तो मैं सॉल्व कर सकता हूँ फटाफट. इन कौन आप करेंगे, आपके साथ देख के मैं सॉल्व कर दूंगा. लेकिन उसमें मेरा कॉन्सेप्ट दिमाग में जल्दी ज्यादा देर तक नहीं रहेगा. कुछ दिन रहेगा, उसके बाद चला जाएगा. जल्दीबाजी में करेंगे तो ऐसा ही तो होने वाला है.
Okay, so I'll check. देखती हूँ ना कि क्या timelines है अभी के लिए. Exact
Yes,
मुझे
ma'am.
भी नहीं
Even
पता है.
that's a problem. We can do it, ma'am, but
for like we need
For
time
grabbing the
to
concept.
digest, ma'am.
Yeah, you need.
Yes, ma'am.
Yes, we can solve it faster, but the concept will
Mm.
not remain for a long time. And quiz will require the concept of us and how much memory we can store in our brain from the contents we read.
I'll discuss with this topic about someone who are, I mean, who is actually know what are the things going on there, and after that I'll let you know in the
But
next session.
but instead of scheduling the end term on 22, they should
Mm.
extend the date at least 1 week. Then all the dates
I
will
mean
not
29.
clash. That's why the
Mm.
dates are coming closer and clashing with each other.
Mm. This clashing of dates happening very
हम्म
frequently in this time.
आप
Week
कैसे
6, week 7.
देखिए 5 दिन में के अंतराल में अगर आपको वीक 7 से वीक 8 में जाना है तो
हाँ पूरा टाइम तो लगता है और वो भी आप लोग पहली बार आई मीन इफ यू आर स्टडिंग फर्स्ट टाइम फॉर दिस लिमिट कंटिन्यूटी डिफरेंशिएबिलिटी इट एक्चुअली टेक्स टाइम्स टू set its base and understand what's actually going, what is happening here.
नहीं देखिए लिमिट कंटिन्यूटी ये 12 बोर्ड्स में भी हमारा था लेकिन यहाँ पे थोड़ा एडवांस है थोड़ा बहुत
हाँ सीक्वेंस के थ्रू डिफाइन करना
देखिए ये तो 12 वाला मैथ नहीं है ये तो ग्रेजुएशन वाला है और आखिर में ग्राफ थ्योरी जो है वो मास्टर डिग्री का सिलेबस है
ग्राफ थ्योरी के लिए आप लोगों को थोड़ा टाइम चाहिए पड़ेगा एक तो उसमें
ग्राफ थ्योरी आप तो ग्रेजुएशन सिलेबस में आप तो नहीं ढूंढ पाएंगे इसको ये तो मास्टर डिग्री का सिलेबस है
हाँ ग्राफ थ्योरी ग्रेजुएशन में भी रहता है आजकल इट्स नॉट दैट डिफिकल्ट ग्राफ थ्योरी फॉर मास्टर्स वी हैव सम एब्स्ट्रैक्ट ग्राफ थ्योरी मतलब वहाँ एब्स्ट्रैक्ट थ्योरम्स वगैरह होते हैं ये थोड़ा ऐसा है कि आई मीन यू हैव एल्गोरिथम्स हियर सो एल्गोरिथम्स आई थिंक इट्स नॉट दैट मच लेवल बट हाँ न्यू टॉपिक है तो टाइम लगेगा दैट मच आई कैन हाँ सही से अच्छे से अगर पढ़ना है कि आई मीन for to understand the whole concept of graph theory you actually need some time.
नहीं जो मेरे जो जाने पहचाने हैं जो आईआईटीज में पीएचडी कर
हम्म,
रहे हैं वो सारे
हम्म,
भैया जो
हाँ
मेरे
हाँ
सीनियर्स है वो भी मुझे कह रहे थे कि उनका मास्टर डिग्री में ही था ग्राफ थियरी
हाँ ग्राफ थ्योरी रहता है मास्टर डिग्री में पर मास्टर डिग्री का ग्राफ थ्योरी में भी काफी सारी चीजें है ना तो जो इनिशियल ग्राफ थ्योरी होता है वो सिंपल ग्राफ थ्योरी जो है वो यहाँ पे है जो मास्टर लेवल में जो ग्राफ थ्योरी होता है ना उसमें बहुत सारा ये तो मास्टर लेवल का आई मीन मास्टर अगर आप वो कोर्स देखोगे ना उसका जो पीएचडी वाले स्टूडेंट बोल रहे थे मास्टर्स का तो उसका अगर आप 1/4 या 1/5 अगर कर लोगे तो उतना सिलेबस है आप so it's not like that the whole master course whatever they taught there in graph theory उतना ज्यादा नहीं है उसका 1/4 पढ़ लो there they will teach you at least I mean if you follow any standard book then they will teach you at least 6 to 7 chapters so here you are just I mean for 1 or 2 chapter you can assume at max yeah so but हाँ time लगेगा that I can say बिकॉज वहां तो आपके पास सेमेस्टर होता है ना उतना बड़ा कोर्स कंप्लीट करने के लिए 6 मंथ टाइम होता है 6 मंथ तो नहीं बोल सकते बट एटलीस्ट 4 और 4.5 मंथ होता है
इवन मैंने
यहाँ
उनको
यू जस्ट हैव
सिलेबस
15 days सो
इवन मैंने उनको सिलेबस दिखाया भी था तो वो भी कह रहे थे कि 3 महीने में करना
हाँ हाँ
थोड़ा
हाँ तो वो
थोड़ा
भी एक चीज है वहां तो 6 महीना होता है उतना बड़ा कोर्स करने
हम्म,
के लिए यहाँ आपके पास सिर्फ कितना दिन 10 दिन बोल सकते हैं ज्यादा ज्यादा 15 दिन मैक्स
मैम
Uh,
इसके पहले
mm,
रीजन चेंज हुआ ना
who's talking
हाँ मैम
your voice is
I'm
not
Anu
clear
मैम या I'm what's wrong
okay so let's start
I'm
hello
audible yeah
Your
I'm
voice is
audible
not clear. No, not clearly to me. If you have any issue, you can message in the chat box. That's also good. So let's start without further delay. I mean, it's already recorded. So I'll start with some basic functions. So basic function means I want to discuss two type of functions here. So first function is modulus function, mod function. Okay. So this is also known to be an absolute value function. So I think you guys are familiar with this function, but let's recall. So if I define a function from real number to real number, in such a way that the expression is given in this form. So that means the value of f of x will be x if you take any point which is greater than or equal to 0. And it will be equal to minus x if you take any x which is strictly less than 0. So that means we are defining a function which has two type of expression respective to the point. So that means if you take any non-negative point, so non-negative means positive point, for example 1, 1.5, 2, 2.5, or 0.5 or something. So any point which is lying right side of the 0. So for all those points, this function is nothing but the value of function is nothing but equal to x. So that means whatever point you will take, suppose 0.5, then f of 0.5 is nothing but 0. But if you take any point which is lesser than 0, then the value is nothing but minus multiplied by of that term. So minus multiplied by of any minus will become a positive value. So that means ultimately here also you will get a positive. So that what does it mean? So it means that no matter what x you will take or no matter what real number you will take, at the end you will just getting a positive number. So this function is known to be a modulus function or absolute value function, and this is also denoted by mod of x. So yeah, so that means modulus of x is nothing but a function defined in this way. So here we can compute some values of function to get the whole idea. So that means f of 0.5 is nothing but equal to, you can write out to be modulus of 0.5 is same as 0.5. But if you take any negative number, so suppose f of minus 1, then this is equal to minus of minus 1, correct? And minus of minus 1 will become plus of 1. So this is modulus of minus 1, and modulus of minus 1 is equals to 1. So I think in your 10th or 12th standard, you have learned about the modulus value, right? So modulus value can be defined using this particular piecewise function, right? So this description you have to always take, keep in mind, because we use this particular piecewise description of a modulus function for calculating the limit, continuity, and differentiability of this particular function. Okay. So this is a modulus function. Now let's consider the graph of modulus function. So here you observe that if you take any point which is lying right hand side of the 0, then this function is nothing but behaving like a line y is equals to x, right? So here we just have x. So that means if you take any point which is lying right side of the 0, then it's nothing but the straight line denoted by y is equals to x, right? And if you consider any point which is actually lying left hand side of the 0, then it's behaving like a line y is equals to minus x. So the graph of line y is equals to minus x will look like this, right? This is y is equals to minus x, and this is the graph of y is equals to x. Okay, so that means on the right hand side we have this graph, and on the left hand side we have this graph. So this is suppose this is straight. Okay, so this is the graph of modulus of x. The graph is also very helpful when we discuss when we want to talk about the differentiability. Okay, so I hope there is no doubt in this particular small functions, just the modulus function, absolute value. Now second function I want to consider is the floor function. Okay, the second function is floor function. So floor function, or this is also known to be the greatest value function, but for time being, we just know about the floor and ceiling function. Okay, so it is denoted by this description, right? So this is the notation for floor function. So what is a floor function? So in floor function, what you have to do, you have to
Greatest integer of x, not greater than x.
Greatest integer function. So in the floor function, what we have to do, we have to consider that integer which is actually which is the greatest integer less than or equal to x. So that means, so f of x is equals to the greatest integer less than or equal to x. So let's try to understand this definition. What do you mean by greatest integer less than or equal to x? So suppose this is your real line. So in real line, you have so many points. So let's spot one point. So suppose there is this point. So let's take it to be a particular value. So suppose this is a point of 2.4. Okay, so this is 2.4. So around this 2.4, there are two integers. So that means there will be some integer which lies over the right hand side and some integer lies over the left hand side. So here, if you consider number line, then this is 0, this is minus 1, this is 1, this is 2, and then 2.5 come in between 2 and 3, and then we have, and so on, right? So what does this greatest integer function or the floor function tell us? So if you have any input, any real number as your input, then it will produce an output which is the greatest integer less than or equal to x. So that means the next integer lying the left hand side of this particular value. So that means you have to consider 2, because 2 is the greatest integer, right? So it is greatest among all those integers which are lying in the left hand side. So that's why greatest integer. So greatest integer less than or equal to x. So we have to choose first integer which is actually lying in the left hand side of this particular value. Okay, so that's the meaning of greatest integer less than or equal to x. Now, similarly, we have one ceiling function also. So this is a floor function. Similar description is also for ceiling function. So ceiling function is denoted by this particular notation. This is only the upper one. So some kind of ceiling therefore refer to our physical phenomena.
Smallest
So if we
integer
have
value
floor, then
greater than or equal to x.
right. So smallest integer greater than or equal to x. Right. So that means if you again consider the number line, so here 0, 1, 2, now here it is 2.4 and 3. So in this scenario, what you have to do, you have to take the smallest integer which is greater than or equal to x. So here, if you consider the, the integers which is greater than or equal to our value 2.4 are these integers, which are lying in the right hand side. So what you have to consider, you have to consider the smallest one, which is lying toward the left, toward the right hand side. So that means if you want the output according to this particular ceiling function, then for this particular input 2.4, the output will be 3. So that means f of, or you can say, that the ceiling function of 2.4 is nothing but 3. So in this case, ceiling function, what you have to consider? You have to consider smallest integer which is greater than or equal to x. So that means the first rightmost integer in our number line. Now here observe one thing. So if you consider x to be your integer, so then the value of function is nothing but that particular integer itself. So that means here let's take some of the examples. So what will be the, so I'll ask you, so what will be the floor function of 0.5? 0. 0, correct? Because 0 is the greatest integer less than or equal to x. But here, if you consider what will be the floor function of 1, then it is equal to 1. So that means over the integer, we are taking the same value. So that means in general, you can say, so if n is an integer, then the floor function of n is nothing but n itself. Okay. And similar for ceiling function. So here we observe that ceiling of 2.4 is nothing but 3. Similarly, you can say what is the ceiling of ceiling value of 0.5? 1, correct? Because the 1 is the rightmost. And similarly, for any integer n, the ceiling function also gives us the value n for all n belongs to integers. Okay. So is there any doubt in these two description, floor function, ceiling function? It's clear, right?
Yes, ma'am.
Now let's try to observe the graph of both of the function. Okay, so suppose this is the floor function. So this is the floor of x. So what will be the graph? So in graph, first thing we know that over the integer, we just have to consider the value itself. So that means if this is 0, this is 1, 2, 3, right? Minus 1, minus 2, minus 3, right? So here the value of function will be integer itself. So that means these, so that means these dots will be there. So here also you will consider scaling, right? So that means these dots always be there. Now we have to consider, we have to look for the values which will be the, what will be the value over this particular interval. So this is nothing but minus 3 and minus 2. So if you consider any point in between them, so suppose this is minus 2.4. So what will be the floor function of this one? We have to consider greatest integer less than or equal to this quantity. That means the leftmost integer. So any x which is lying over this particular interval minus 3 to minus 2 will take the value minus 3. So suppose this is minus 1, minus 2, minus 3.
You return the floor function as ceiling.
This is a floor function, no?
No, the symbol I'm saying.
Oh, sorry.
Okay, ma'am.
Floor function. So here what we have to do, we have to consider those value which is, if you consider any x which is lying between minus 3 and minus 2, then the floor function for that particular x will take -3 as its output, right? -3 will be the value given by the function. So that means over this interval, all the points are taking -3 value. So that's why the graph of this particular floor function for this particular interval -3 to -2 will become a constant value -3. So that's why the graph will look like this. And similar observation you can do for any x lying between -2 and -1. So the graph will look like this, like this, like this. And here we know a general description. If there is one hollow point, so that means the value of function is not. So this is the graph of function for floor function. Okay, now similar graph we have for ceiling function also. But in ceiling function, what happened? Just observe the graph. So suppose I have a ceiling function. So now this is the description for ceiling function. Right? Sorry. I have written the symbol correctly, right?
Yes, ma'am.
Yeah, correctly. Yeah. So now for ceiling function, what is the thing? So again, over the integer points, we have the same values. So that's why these dots will be there. Now we just have to figure out if we take any point in between the integers, what will be the value? So suppose this is your -3 and -2. Again, if I take any point in between them, so suppose -2.4, then what will be the value here? What will be the ceiling function? Here we have to take the rightmost value. So that means over this particular so that means the ceiling value of -2.4 is nothing but -2. So that's why if you take any real number x in between -3 and -2, the value of function in case of ceiling function we will get -2. So that means any x lying in here will take -2 to be as its output. So that means this is the graph of ceiling function. Similarly, you can consider for every vertex. Okay, so I'm leaving the all other points for you guys. Okay, so see, there is a little difference between a floor function and ceiling function. So observe that here, so you can understand by seeing. So if a graph is given to you, so just try to consider the graph around 0. So you can easily judge is this the graph belong to the floor function or the ceiling function. Is there any doubt in the graph? How we constructed the graph? So I'll recall. So first we know that the integer values will be there. So that's why we put the dots over the integers. And then we consider that if we take any point in between that integer, then what will be the value of function? So just that particular constant you have to take and answer. Sorry, your voice is not clear. Whoever is talking. Okay. So now let's go to the definition of.
Hi, could you hear me?
Yes, yeah.
You said like when it comes from 3 to -1, the constant it's always -3. Am I right? For the floor.
Right.
So it's like anything less than whether it's -2 or -1, it will be the same. -3 is it?
It will be the same. That's the thing. We always have to consider output to be an integer. So that's why over this particular interval, the value will be the constant -3.
Okay, and maybe I because I just joined some in the later part, almost like 15 minutes later. So when it comes to more than -3, what will be the case?
More than -3 means here.
Yeah, what will be the value there? Because you said
then -4 will be there. So that means something like this. So it will increases over here and all other points.
And here maybe again it's for the infinity and minus it will be infinity, right? Yeah.
Sorry, what?
For the infinity and minus infinity in both the case, if that's the case, like what will be the here?
No, actually infinity is not a value for us. Infinity is just a symbol for denoting we are considering a large value. So we won't bother about what will be the value at infinity there. So that's the case. So infinity is not a number. So don't ever treat it.
Yes.
So that's why we don't bother.
I want to clarify my doubt, so I thought I
Yeah, it's good.
Thank you.
Because if you don't think what will be the case, then it's very hard to learn maths. How to think. Okay, so these two functions is actually very interesting when we want to talk about differentiability and continuity. So that's why I first covered this. And now let's go to, I'll just give a quick recap about what is the limit. So because the definition of continuity and definition of differentiability both involve a particular kind of limit. So if you are not comfortable with limit, then it is actually very difficult to understand continuity and differentiability. So let's go via the limit first. So limit of a function at particular point. Yes.
I mean, 12th standard, we have studied about the step function, which you have previously.
It's
So
also
the
known to be
floor,
as a step function.
floor,
Floor
is it
function.
floor or ceiling, no? Floor.
I think both function are known to be the step function. So that's why I haven't used the word step function here. Because what is happening in both function, the value is jumping one step ahead. Right. So here also the value is jumping one step ahead. So that's the
One step
another
below,
reason it's
right?
known to be one step. Yeah, correct. Sorry, one step below. Because on 0 we have minus value here. Yeah, whatever, this is one step ahead. Below you guys will figure it out. But that's why I haven't used the step function name, because then it won't be clear which function we are considering. Okay, so let's talk about limit of function at particular point x is equals to a. So for limit, we use the description of left hand limit and right hand limit, because here we are in real numbers. So if you consider a real line, then on real line, for approaching any point x is equals to a, we have two paths. So one path is we can reach that point from the left hand side, and another one is we can reach that point from the right hand side. So what's our motive in terms of limit? So we want to know that if we approach our point from left hand side or right hand side, where does the value of function goes? Right, so that's the motive of limit. So that's the thing we want to find, that if you approach your point from the left hand side or from the right hand side, where the values of function goes. Okay, so that's the main purpose. Now, how we define limit? So we define the limit of function at any point using the sequence. Sorry.
Okay, yeah, can you please repeat once again? When we are moving from left hand side to right, I didn't get the part.
So here, see, the direction seems to be that we are going toward left hand side, but this is the left hand side of the real. I mean, this will be the left hand side for this particular point, and this will be the right. This will be the right hand side for the point x is equals to a, and this will be the left hand side for point x is equals to a. Okay. So if you approach this point from this direction, so that means considering all the points which are lying over the right hand side, then here whatever limit you will get, that limit is known to be right hand limit. So what is our main aim here is to observe the behavior of graph as we approach our point from these two directions. Is that clear?
Yes.
So what is the definition of a limit? How we define a function as a limit at particular point? So we use the concept of sequence. So I think you guys are familiar with sequence. So suppose if you have a sequence an in such a way that this sequence an is actually converging to point A. Okay, so we have a sequence which is converging to point A. Then what do we want? So we want to observe that where does the functional value sequence. So functional value sequence means if you apply f over this all these ans. So again, here we observe, trivially take that all the en belong to the domain of function. So that application of function is valid here. So if you apply f over all these points an, so then you will again construct another sequence known to be f of an. So what do we want? We want to know where does this sequence f of an goes. Okay. Function if it goes to a finite value. Okay. So that means, and this should happen for every sequence, no matter what sequence you will take, which is converging to a. For every sequence, if our function f of an converging to the same value L, so that means if you what you can say, change the sequence, still the convergence or the point limit point for f of an will be same L, fixed L. Then this particular L is known to be the limit of sequence. So that means if so here, if for all sequences an, such a way that an is converging to a, we have the sequence f of an converging to a fixed value L. The cell is fixed value L. Then we say that limit of function at that particular point exists. Then, and denoted by this particular notation. So limit x tending to a, f of x exists and equal to f. Okay, so this is the formal definition for defining a limit of function. So here conceptually, or if you want to understand the whole picture, what we want to do, we want to construct, for every sequence which is approaching to A, we are saying that our sequence f of A, the value of, if you construct the sequence f of A, then that sequence is actually converging to a fixed point n, no matter whatever sequence you take in place of A. So if this particular type of scenario happens, then we say that limit of function at x is equals to A exists. And what will be the value of limit? So the value of limit will be equal to N. Okay, so this is the definition. Is there any doubt in this particular definition?
How an is approaching to A, because an is the sequence index.
So an is approaching, so that means limit of the sequence an is equals to. So you know that limit definition for sequence, right? An approaches to it.
An is approaching.
So for example, if you have a sequence 1 by n given in this fashion, so 1 by n, so we know that this sequence goes to 0. So that means limit of sequence you are saying. So here an approaches to A means the limit of sequence an. So that means limit n goes to infinity, an is equals to. So that's the mean. Fine.
Okay, ma'am. Okay.
Yeah. So
Suppose we have other sequence.
actually, hello.
Yeah. Can you elaborate the other example, like natural numbers or even numbers, odd numbers, something like that?
Okay, about the example. So yeah, so that's the one thing I want to mention here, that we won't use this particular definition to compute any of the limit. So it's just for your reference how we started discussing limit. So we never use this particular definition. It will be a very rare chance. So that means 101, you can say, when we use this particular definition of sequence to compute a limit. Because here what is happening, you have to consider all the possible sequence which are converging to it. So it's in application, it's very hard or very tough, you can say, to use it, right? So that's why we go to the concept of left hand limit and right hand. Okay, so now let's look at what is the left hand limit and right hand. So again, in left hand limit and right hand limit also, we consider all the sequences, but here via the graphical method or via just by observing the expression of sequence, we can easily check that what is the left hand limit of sequence and right hand limit of sequence. So left hand limit is nothing. So if you approach your point from the left hand side, then whatever the value of function approaches, that is known to be your left hand limit. Okay, so left hand limit means if again, it defined via the sequence only, but it's very easy to compute when we come to the left hand and right hand. Okay, so suppose if a sequence an in such a way that an approaches to A, and an is actually the point lying over the left hand side of A. So that means an is less than equal to A. So then if f of an goes to L for all sequences an, then L is known to be the left hand limit, and it is denoted by this symbol, that x approaches to A minus f of x is equals to. Don't bother about this definition for now. So I will give you some other description where actually we uses this definition to prove the limit of very fundamental function. Fundamental function means if you have constant function, linear function, quadratic function, those things. But for computation, for the limit of a very large function or any distinct kind of function, we need some other description. We need this only, but we want to collaborate all the function together so that we can apply. So let's see. So what is the right hand limit?
Ma'am, if we take the limit extends to a minus of c is a constant term, then the limit will become as c.
Then limit will be c, because no matter what sequence you will take, here you always get a constant sequence in this particular scenario, if you consider a constant function, correct?
Correct.
So if the sequence an in such a way that an approaches to A, and an is actually lying over the right hand side of A, that means an is greater than or equal to A, then if, again the same scenario, then if f of an approaches to L for all, this is sign for all, okay? So for all sequences an, then L is known to be the right hand limit, and it is denoted by limit x going to A plus of f of x is equals to L. Okay, so that's all. These are the precise definition of limit, how we actually what you can say describe this particular scenario, that where is our function going, right? This particular scenario, if you want to describe, then we use the help of sequences and define what is the limit, what is the right hand limit, and what is the left hand limit. And this is a very well-known result. So if left hand limit and right hand limit exists and equal, so that means and left hand limit equal to right hand limit, then we imply that the limit of function exists at particular point A, so at x is equals to A. So then the limit extending to A, f of x, also exists, and it's equal to the left hand limit and right hand limit. And left hand limit is equals to right hand limit is equals to the limit of function, limit extending to A, f of x. Okay, so now let's try to understand. I think you guys know that if we consider this limit, so what will be the left hand limit for constant function? Limit x going to a minus of a constant function c is simple c, because no matter whatever sequence you will consider, if you apply function over there, then at the end you will just get the constant function. So that's why. And similarly, the right hand limit is also equal to c. And so using these two limits, we can say that the limit x going to a, the constant function, that means f of x, which is actually equal to limit. So here we are discussing about f of x is equals to c, constant function. If you think I'm moving too fast, you can interrupt. Okay. Limit x going
Yes,
to
ma'am.
a,
Yes,
c
ma'am.
is equals to c. Okay, so this is for constant function. We know that if we take a limit for any constant number c, then the limit is actually equal to the value c itself. Now let's take another case, and that will be the linear function. I mean the basic y is identity function. Okay, so if we have identity function, that means f of x is equals to x.
Ma'am,
Then
I forgot the condition where we used to check right hand limit in equality with the left hand limit. For which
so
purpose?
yeah, for saying that the whole limit exists.
Hmm.
If the right hand limit and left hand limit are equal, then you can say the whole limit x going to a, f of x will exist, and it is actually equal to the value of right hand limit and left hand. That's
Okay.
why we use this.
But
Okay.
it sometimes it for constant function and for sometimes for the square function. Otherwise,
I mean,
it will not come.
no, it will come. Left hand limit, right hand limit concept will come. Let me proceed. Okay. So suppose if you consider identity function, then in this case, we can easily compute what will be the left hand limit and right hand limit using the description of sequence. Okay. So here, what will be the left hand limit? F of x is equals to limit extending to a minus f of x is there. So can you guys give me the answer? What will be the value here?
What is identity function?
F of x is equals to x.
F of x is equal to
Okay. So
What
it's
will be left
limits.
hand limit and right hand limit?
It is 1.
1? Sure. I mean, here I am considering any random point A.
A, both are A.
Both
Okay,
are A,
same
correct?
point.
Same point, na?
Uh,
Because the sequence AN, so
yeah, ma'am, Indra here. A quick question. So you said this is an identity function. Why is this an
yeah,
identity?
sometimes it's known to be an identity function because it's giving the same value. Now, if you put 1, then it will give you 1. If you put 2, it will give you 2. So that's why it's known to be an identity
That's why it's called
function.
identity. Okay. Thank you.
So why these two limits are equal to A? Because if you consider any sequence AN converging to A and apply f over the sequence, that means f of AN. So since it's an identity function, that means the description is f of x is equals to x. So the value of f of AN is nothing but AN. So that means after applying function over this particular sequence also, we are getting the same sequence. And since AN converges to A, so this AN is also converges to A. So because of this reason, these all two limits are equal to A. Is that fine?
Yes, ma'am.
So it's a description is I mean the sequential description of limit we use this for such a simple function. But what happen if we have a polynomial or if we have a rational function? Then in that case, what we do? Okay, so let's try to understand. So in this case, we apply the arithmetic of limits. Arithmetic of limit means, so if an limit of f is some L and limit of function g is some another number, then what will be the limit of addition of these two functions? Okay. So I want to spend a little time here because if you understand limit properly, then there is nothing in continuity and differential.
Samita, I have a doubt. Sorry, I haven't worked on the fundamentals a lot. So,
Okay.
with regard to the limit function that you said, where the right hand limit and left hand limit, so when is the case that they will be equal, and when is the case that they won't be equal?
Yeah, so yeah, we can understand that by graphically easily. So suppose I'll consider two functions. So example. So suppose you have a function whose graph look like this. So this type of question will be there in your assignment, I guess. Suppose something like this. This is your function. Again, we are using the convention that if there is a solid point in the graph, then the function value is here, not the hollow point. Okay. So suppose the graph of function f is this. Then can you guys compute the left-hand limit at point 0? So this is 0, 0. Then what will be the left-hand point? Limit x going to a minus of f of x. And what will be the limit x going to a plus f of x?
Minus
A
a.
minus A
So left-hand
minus
limit will be?
This is
Minus
linear
a.
function.
Left-hand limit will be?
F of x is linear
Minus
function or
five.
a exponential?
No, you don't need the expression of function. By the graph only you can see.
It is minus 5.
Minus 5. Correct. Why it is minus 5? Because if you
Because it's just
approach
Yep.
approaching toward minus 5, right? So if you approach your point 0 from the left hand side, then where does our function go? So function is actually approaching the point minus 5. So that's the thing you have to look for left hand limit and right hand. So if you approach your point from the left hand side, where does your function goes? So in this case, as we approaches to a point x is equals to 0 from left hand side, the value of function is actually going closer and closer to minus 5. Right? It is not exactly minus 5, but it is reaching toward minus 5. So this reaching behavior or tending behavior we want at limit. We actually don't want the precise value at that particular point, but we want where this particular function goes. Okay. So that means what value is that where this particular function will become very closer and closer to this one. So if you consider any value which is actually very near to 0, so suppose this value, which is actually very near to 0. So this at this particular x naught, if you compute the value of function f, then that value is actually very closer to minus 5. Okay, so this particular behavior we want to observe in case of limit. Is that fine?
Yes, ma'am.
Okay. Now what about the right hand limit?
It will be equal to 2.
2, correct? Because if you approach this particular point 0 from the right hand side, the value of function is actually getting more closer and closer to the value 2. So that means if you consider any point very closer to 0 over the right hand side, the value of function will be very close to 2. Okay, so this type of scenario we want when we consider the limit. Is that fine?
They should be the whole one now in the upper 2, because it's that this means that it approached to 2. I mean,
It is approaching
maybe.
to 2, so that's why right hand limit is 2 and the value of function is also 2. So that means f of 0 is equal to 2. So that's why this this solid point is here.
The function reaches limit at some point.
So that means in this case, what is happening? Left hand limit is not equal to right hand limit. So here we can say that the limit does not exist. So that means limit of function f at x is equals to 0 does not exist.
Because if it reaches, then the value will be 2.
So it is actually reaching toward two distinct points, right? So that's why in this case we say that the actual limit does not exist. So if someone gives you graph and if they want to talk about limit, I think it's very pretty clear that you guys can judge, right?
Hello,
You
ma'am.
just have to consider. Yes.
Ma'am, I have just one doubt in this. So let's
Hmm.
consider in the same graph, let's consider a point minus 1 comma 0.
Minus 1 comma 0 in this particular graph here. Minus
Yeah,
1.
same graph. On x-axis minus 1. 0.
Okay. So the limit point you want to change.
Yes, ma'am.
So x is equals to -1 you want to consider. Now what?
Yeah. So in this condition, how to prove the limit, or how we conclude,
So
make a conclusion
suppose,
about the limit at -1?
okay, so now you will answer. Okay, so I'll ask you a series of questions. So if you approach, so suppose at -1 the value of function is something. So suppose the coordinate of this point is nothing but -1 comma -4 type something. Okay, so now here, so if you approach x is equals to -1 from the left hand side, where is actually your graph going?
At 5, -5.
At -4, right? So this point is -4.
Okay, -4. Okay.
So this point you have to consider, whatever the intersection here. So this point. So that means if you approach x is equals to -1 from the left hand side, the value of function is actually approaching to -1, correct? Now similarly, if you approach the point x is equals to -1 from the right hand side, then where does your value, what will be the value there? If you
-4.
consider the right hand, then -4
Yes,
will be,
-4.
correct? Because
Yes.
if you come from this direction, then also you are approaching -4. So in this case, the left hand limit is -4. The right hand limit is also -4. So that means both are same. So we can say that limit x going to -1, f of x exists, and it's equal to -. Okay, fine.
So it means for continuous function, limit always exists at particular point.
No. That's not the case. You're saying, the reverse one. What is the continuous function? So for defining continuous function, we want that limit should exist there. So you cannot say that this is a whatever you're saying is correct, but for proving continuity, we want this limit to exist and equal to the function.
Okay. Yeah. Thank you, ma'am.
So,
are there any terms to define the equal limit and unequal limit?
no, actually, for one dimension we don't have. If you go to higher, multivariable calculus or somewhere there we have other description. But for this particular real number case, we don't have. We just have right hand limit, left hand limit. If they are equal, we say that limit of function exists. If they are not equal, we simply say that limit of function does not exist.
Ma'am, one doubt. You have written like limit extends to a minus f of x equal to -x, and limit extends to a plus f of x equal to 2. Here a equal to 0, right?
Here a equal to 0.
Okay.
Right. Fine. So now, as we computed the limit for these two simple functions, constant function and f of x is equals to x, now what we can do, we can use some result to get limit of more complex functions, which are actually made from these functions. Yes.
So, this portion actually is very clear. Where the sequence come into play here? You started the session with sequence. How we can correlate the sequence and the mix here?
So see, if you graphically think, then what we actually doing here, so we are actually considering the sequence only. Here, if you graphically approaching your point x is equals to -1, then you are taking some values, right? And then you are approaching. So these values are actually denoted by the sequence here. And this sequence is actually going to -1. And then we are looking what are the functional values. That means f of a. Where does the sequence goes? So yeah, this is one thing you can consider. Fine. So yeah, what I was saying that since we know the limit for two simple function, we can actually use some algebra of limit and try to construct what will be the limit for those functions which are made from these two functions. That means if you add them, multiply them, take a power, take a quotient or what. Okay. So that's known to be algebra of limit or arithmetic of limit. So let's consider what are the rules. Similar rules we have for differentiable function also. So it's better to understand here. So here first we suppose that we have two functions whose limit is known to us at some point x is equals to. Okay, so suppose we have two functions f and g. So suppose f and g are two functions. And we know the limit of f and g at particular point a particular point A. So that means, and limit extending to A, f of x is equals to, suppose I'll name it to be L1, and limit extending to A. So here observe that the point is same. Okay, so limit extending to A, g of x is also equal to L2. Okay, so we have two functions whose limit is known to us at certain point x is equals to A. So if we know this particular information, then we can actually conclude several things. So first thing is that if you multiply any constant to any of the function f or g, then the limit will become just constant multiple of that limit. So that means limit extending to A, c of f of x, this particular limit is same as c times of L1. Okay. The second thing is the addition or subtraction. So that means limit extending to A, f of x plus minus g of x is actually equal to L1 plus minus L2. Same thing happens for multiplication also. So limit extending to A, f of x multiplied by g of x is actually equal to L1 multiplied by L2. Now for quotient, we need to consider one constraint. So that constraint is L2 is not equal to 0. So that means if L2 is not equals to 0, then limit extending to A, f of x upon g of x is equal to L1 upon L2. Right, so these four rules are there. Now using these four rules, we can actually compute what will be the limit for polynomial functions and rational functions. Okay, is there any doubt in these rules? I think it's a very
Ma'am,
pretty straightforward.
Ma'am, a quick question. So when you
Hmm.
wrote that limit x tends to A, f of x tends to L1, just a
Hmm.
conceptual question, that when we say that x tends to A, does it mean that
Hmm.
we are traveling from left to right towards A, or from, like, what are we saying here is trying to just understand.
This particular description means we are traveling towards A, no matter which direction you want to consider. Yeah, we just have two directions, so that's why it means you can travel at any direction, using any direction.
Oh, got it. So that's why it's said that limit can only exist in a continuous function, because either way we approach, we always decide at one point.
Always get the same point. So yeah,
Got it.
that's why if left hand limit, right hand limit equal, then the value is equal.
Okay. Thank you.
Ma'am,
Yes.
ma'am, suppose in the place of f of x, I consider x square for the case 4,
X square.
and in place of g of x, I consider 1 plus x, then the value of the limit will be
L1, L2. So that's the thing we will discuss now. So suppose you have, so now no matter what you, you just take this particular example, right? X square and 1 plus x. So in place of that, if I take a general polynomial, so suppose I have two polynomials, E of x and Q of x of degree n and n. So suppose this is a polynomial, a n x to the power n plus up to a1x plus a. And this is another polynomial, bm x to the power m plus and so on up to b1x plus b. So suppose these are two polynomials, and suppose we have a point x naught, so that x naught is any real number. Then here, by combining these results, because we know two things. So what do we know? So we know that limit x going to x naught of any constant number c is actually equal to c itself. Right? We know this limit by sequence, and we know this limit, that limit x going to x naught of identity function x is actually equal to x. And we know these four rules. So what we can do, we can combine these two things and answer what will be the limit here. Okay. So let's just try to observe what will be the limit in this case. So limit x going to x naught, p of x. What will be the limit? So what we do here, we can actually distribute this limit over the constant term and the multiplication and the scalar. So that means this is the case, a x plus a naught. So this is same as an we can take common because it's just a constant by the first rule, right? What the first rule says, that c of f of x, the limit will be c times the L. Okay, so an we can actually take common, and here you can say that limit x going to x naught of x to the power n plus again an minus 1 will be there, and the limit will be there, and so on, plus a1 limit x going to x naught of x and then plus a. Right, so this is same as actually an, and we know that because of this condition, limit x going to x naught, x is equals to x naught. So here, if you consider limit x going to x naught, x to the power n, no matter what power you will take, it's actually equal to. Obviously here, since this is the polynomial, so here n and m belongs to natural. Don't consider it to be an integer. They are natural numbers. So here, if your n is a natural number, then this limit is nothing but x naught. Is that fine? Because we are just multiplying, right? And in the second rule, we observe that if you multiply two functions and their limit is known to us, then the multiplication limit of two function is nothing but the limit of multiplication of their limits. Fine?
And could you please elaborate on this? I mean,
This one is not clear. How did you come up with that
Okay.
x naught?
Okay, so let's try to take a particular example. So,
Yeah.
because this abstract thing will be a little boring. So suppose I have a particular example. So let's take it to be 4-degree polynomial. Okay, so if I have a 4-degree polynomial, then how can I compute the limit of that particular polynomial? It's a very simple result, but it's better to understand how we use it. Okay, so suppose you have a polynomial p of x. It's nothing but 4x to the power 4 plus 3x square plus 2x plus 1. Okay, so it's a 4-degree polynomial. Now here, if I give you a particular point, let's take it to be x is equals to 5, and ask you what is this limit, that limit extending to 5 of p of x. So that means limit extending to 5 of 4x to the power 4 plus 3x square plus 2x plus 1. What will be the value of this limit? So what you do, in general, you just substitute x is equals to 5. But here, I think you guys are known from your 12th standard or 11th standard. We just take x is equals to 5 and answer it. But in some question, what happened? In some question, they said that you cannot put x directly. So here we want to observe that why we can just, in place of x, just replace x with 5 and get our answer. So why this thing happened is, the reason is the whole concept behind it. So that means, so what will be this limit? So this limit is nothing but, what you have to do, we have to, since we know that the limit can be distributed over addition. So that means this particular rule. So what does it say? That limit of f of x plus g of x is same as limit extending to a f of x plus limit extending to a g of x. So that means we can distribute limit over addition, subtraction, multiplication, and division. But in division, we just have to consider that the limit of denominator function is not equal to 0. Okay. So here what we can do, we can distribute our limit over these 4 parts. So that means now we can say that this limit is actually equal to limit x going to 5, 4x to the power 4 plus limit x going to 5, 3x square plus limit x tending to 5, 2x, and plus limit x tending to 5 of constant value 1. Right? Now it's a little easy to compute. Correct? Now, but we know another result which says that you can actually take this this constant out of your limit. That's the thing. This particular first result says to us that limit extending to a of c of f of x is c times limit extending to a of f of x. So that means you can actually take this particular 4 common, or we can pull it out from our limit. So this limit will be same as 4 times limit extending to 5 x to the power 4 plus 3 times limit extending to 5 of x square plus 2 times limit extending to 5 of x, and plus here again it's just a constant number, so that means this limit will be equal to what?
The c.
So what is the value c here? 1.
1.
Right. So now what is our task now? Our task reduces to compute the limit of these particular functions. But what are these functions? These functions are nothing but some power of x. Correct? And we already know that limit extending to x naught of x is equals to x. So if you take any power of this particular thing is nothing but the power of x naught. So that means for any natural number, we know that limit extending to x naught of x to the power n is simply x naught to the power. Because of the multiplication, we are just multiplying x n times and we can distribute the limit. Is that fine? This particular remark?
Yeah. This is fine. I think previously when we wrote it, then it was like x 10 to the power n was converging to x naught. That's where the confusion rose.
Yes,
So
because
that
we
means
are
this
putting the
is
value x naught in place of x, because extending towards x naught.
x naught. So because of this thing, because we know this particular limit and we know that we can actually distribute limit over multiplication. So that's these two results combiningly say that this particular limit is equal to x naught to the power. So the result, so here it becomes 4, and here what we have to do, so the value x naught here is 5, so that means 5 to the power 4 plus 3 times 5 square plus 2 times of 5 n plus 1. And which is nothing but, if you observe that this is nothing but p of 5. We are just substituting in place of x, we are substituting 5. Is that clear? This whole example?
Yeah, this is clear. Yeah, thank you.
Ma'am,
So
I'm
the
having a
result is
question,
very
ma'am.
simple.
Like
Yes.
similar to this, but it's graded assignment of 7. Can I tell?
Yeah.
Limit an tends limit of n tends to infinity of an,
Okay.
where an is equal to
Okay.
12n square
Hmm.
divided by 3n plus 27
You asked this
minus.
question. I mean, some similar type of question is done in today's TA session, if I'm not wrong.
Oh, I'm not aware of that.
Minus of
4n square plus 23 by n plus 5.
Okay, so you want to compute the limit, right?
Yes, ma'am.
So here what you do? So first of all, just take the LCM of these two terms. So that means take this particular term, 3n plus 27, and here it will be 5. Sorry, n plus 5. And here it will become 12n square multiplied by n plus 5 minus of 4n square plus 23 multiplied by 2n 3n plus 27, right? And solve it. After once you solve it, then what will happen? So here this particular n cube term will get cancelled out. You will get some expression here in terms of n square.
24 will be the answer, I think.
24 or 54, something like this.
N plus
So
15.
that
Minus
means,
16 was the answer, ma'am.
Minus 16.
okay, minus
Oh,
16.
n plus 5 here. My question can n plus 15. That's why my answer is different.
No problem. Yeah.
So
And
what
in place
you
of 23,
do, and okay, so what you do, just simplify the numerator and denominator. You will get some polynomial in n square. In the denominator also, you will get some polynomial in n square. And we know how to handle such kind of limit. We just pull out the greatest power of n, and then look where using this particular limit, that limit n goes to infinity, 1 by n is equals to 0, right? Then just
Ma'am,
distribute the limit. You will get
yes, ma'am. I understood this method. What I have done is I have divided the limit limit extends to 12n square is one limit, and minus of limit extends to infinity of 4n square another limit. Then I have applied L'Hospital, and I got like 0 as the answer.
No, one thing is here is you apply L'Hospital, right?
Why can't we apply L'Hospital? My doubt is that, ma'am. Like for separate limits, if we take out separate limits, infinity by infinity is coming. It is satisfying. If I am applying L'Hospital, I'm getting 0 answer. But answer like why it is wrong?
No. So one thing is here that, see, here we distributed limit only when the limit are finite. So that means one thing here you have to observe, that if limit of a sequence n is a, and which is finite, and limit of a sequence bn is equals to b, which is again finite, then only you can say that limit of sequence an plus or minus bn is equals to a minus b. But here what is happening? If you do that, so first thing what you have to do, you have to distribute your limit over this particular bracket, correct? So then only you will apply L'Hospital rule. Am I correct? Because here you are getting infinity minus infinity. If you consider this to be your first sequence an, this to be your second sequence bn, then limit of this sequence is infinity, because here we have n square in the numerator. Here also we have n square. So that's why the limit will be infinity. So whenever you have infinity minus infinity kind of situation, or infinity plus infinity kind of situation, you cannot just distribute limit over this whole bracket. That's the one thing. So that means if you want to compute limit of an, so that means you are computing limit of this particular bracket, right? 12n square by 3n plus 27 minus 4n square plus 23 by n by n plus 5, whatever this is. So first thing what you have to do, you have to distribute this limit over this particular guy and then this guy, right? So this is only possible if these two sequence converges to a finite. You're getting my point, what I want to say?
Yes, ma'am.
So here this is not happening, because this sequence 12n square upon 3n plus 27 is actually going to plus infinity, and this sequence is also going to plus infinity. So here you are getting infinity minus infinity kind of situation. But again, as I say, that infinity is not a number. So you cannot say that infinity minus infinity equal to 0. No, this is not true. Because infinity is a way to denote a very large number. Okay, or a way to denote the possibility of a large number. So that's why infinity minus infinity is not equals to 0. So that's the reason I think you are getting 0 as your answer. Because you distributed the limit and then apply L'Hospital rule, right?
Yes, ma'am.
So
So
this thing
now
we
I
cannot.
understood, so that if we are getting indefinite terms, then we should not do such
Distribute
activities.
the limit. First try to simplify a little bit and then apply, then distribute.
Okay, ma'am.
Ma'am, I have sent you one
Yes.
question in the chat box. Please see it and give me some hints.
Okay. So this is the last question. After that, we will return back to it. Okay. So yeah, this question is there. So find the
this
limit of
question's
sequence.
formula is not given in the lectures given by the professors.
Okay, so now it's 9 plus 15 plus. So this is actually a part of series.
Yes, it's the part of series.
But you can simplify it a little bit, I guess. Because
Just
it's
for first term into common difference, that kind of formula, I think we have to apply.
Something like this we have to apply.
Ma'am, have you referred any book which will give us complete knowledge and concepts?
No. There is no book. I mean, first thing, you don't have that much time to go through a whole book. So.
But देखिए ये lectures और जो
There
textbook
you need to
provided है वो
take 3 as common, and then you need to solve the
You need
problem.
to apply some formula that this 1 plus 2 plus and so on
Yeah,
plus n
if you
is
take
actually
3 as
2n
common, you will
divided
get 1 plus 3 plus 5.
by
Like it is sum of odd terms. So
odd
sum
term,
of odd
something
terms is
like
like n
this.
square. N square by n square is 1, and you have taken 3 as common, so the limit will be 3. Answer is.
Okay. So that's how you have to apply. I mean, you have to apply, consider this type.
odd terms sum is n square only.
Yeah, sum
I
of odd
guess
terms
so.
is n square. You
Or
can
n
check.
square or n square minus 1. I written n square minus 1.
No, it is n square.
You
n
can
square
compute it
minus
from
1.
here also.
Yeah.
Because
It's n
okay,
square
let's
minus 1.
okay, guys can check on the Google. Is that fine? You just check it at n square minus 1 or n square.
But ma'am, please prefer a book ना, क्योंकि concepts
For
clear
book,
नहीं हो रहे हैं.
I'll say Tom Apostle देख सकते हो. But again, वो book पढ़ने के लिए at least you need
Oh,
3
actually it
months
is n
at
square
least.
only. You can Google it. Sum of n odd numbers is n square, not n square minus 1.
So if it is n square, I'll get a 2, 4, 6, 8, 10, right? N square minus 1, just
No,
you
you are
written
not
as
getting the concept. For suppose 1 and 3, what are the sum of 1 and 3? It is 4. It is 2 square is 4, like that. 1, 3, 5. So it is 9. 3
Sum
square
of
is
odd
9.
term is different.
Oh. Got it.
So don't get confused.
Okay, so
That's
let's
why
back to
concept
our
is
topic.
important.
So what we are discussing, limit of a polynomial. So what we conclude at the end, we conclude that limit of any polynomial is nothing but the value of polynomial. P of x is equals to P of x. Is there any doubt in this particular thing? No, I guess. So now let's go to the limit of rational function. So suppose you have two polynomial P of x and Q of x, and if you want to compute the limit extending to x naught, P of x upon Q of x, then what will be your answer? Okay, so for solving this problem, what we do, so we know that we can actually distribute our limit only if Q of x naught is not equals to 0. So we can consider two cases here. So the first case will be if Q of x naught is equal to 0, and the second case will be if Q of x naught is not equal to 0. So if Q of x naught is not equal to 0, that means the value of polynomial at that particular point is not 0, then we can actually say that this is nothing but the value P of x naught upon Q of x naught. Because then what happened? We know that this limit is P of x naught. We know that this limit will be, I mean, if you distribute the limit, so we know that limit extending to x naught of p of x is equals to p of x naught, right? And same thing for q of x will be q of x naught. And if we know that this is not equal to 0, then we can actually distribute our limit by this particular fourth rule, right? Here we consider the fourth rule, the addition, multiplication, and then division. So here, if you apply that rule, then you will get limit to be equal to limit extending to x naught of p of x upon q of x is equal to p of x naught upon q of x naught. But here, if you get in the denominator, if you will get 0, then what you have to do, you have to look for a factor x minus x naught in the numerator and try to cancel it. So that means try to factorize and then calculate the limit. So that's how you have to proceed for rational function. Okay, is that fine?
Ma'am,
Now
I have
let's
one
go to
doubt.
the and if it is not factorizable, so that means the limit will depend on p of x and q of x nature. So that means if p of x has higher degree, then it will go to infinity and all those things. You can judge by looking at the expression.
Ma'am, if the denominator is 0, the below quantity q of x not gives 0, then we have to go with the factorization.
Right, we have to go with the factorization. If you
How?
get any common factor, then you just cancel it out and then compute the limit using this particular form. Second one. So
Ma'am,
for
I have one
example,
doubt.
An example?
yes. Okay, someone has a doubt, but
Yeah, yes, ma'am. Consider f of x is equal to 1 by x.
1 by x. Okay.
So here limit
Here
extends
p
to
of okay.
0.
So here limit extending to 0. So now
So
here what is happening?
can
so
we say
this
like
is
it is
actually
discontinuous or continuous?
it is actually discontinuous. So we will come to that.
Okay.
But here also, if you want to find the limit, then you can consider the first one to be your polynomial p of x. P of x equal to 1. And this is your q of x equal to x. And here, if you consider limit x going to 0, then what is happening? Q of x is actually equal to 0. That this limit is equals to 0. So that means here you cannot just simply say that, okay, 1 goes to 1 and x goes to 0. So the limit will be 1 by 0. So here the limit is actually not defined, or infinity, someone says.
Yeah.
Okay, so limit x going to 0, 1 by x is, I actually cannot say this. So I can say that as x goes to 0, this 1 by x goes to infinity.
Okay.
So this is 1.
1
so
by x.
I hope 1 by x is what?
It will go with undefined now, because in the both domain it's going to positive and negative.
Negative infinity. So continuity is not there, but yeah, it's also depend on where we actually approaching 0 from. Here, if we approach 0 from right hand side, because
Yes,
the
ma'am.
graph of 1 by x look like this. So if you approach from right hand side, it goes to infinity, and left hand side minus it. Okay. So now go to continuity. Continuity of a function. So if the value of limit is equal to the value of function, then we say that this function is continuous at that point. Okay, that's easy. So if the limit, so that means limit extending to a, f of x is equal to f of a, that means exists and equal to f of a, then f is continuous at a. At x is equals to a. Okay. So now that's how we say that every polynomial is continuous, because we just see that limit extending to x naught of any polynomial p of x is equals to p of x naught. So that's why we say that every polynomial is continuous.
How we can say this?
Because the limit is equal to the value of function. We just prove a remark, right? That for polynomial, limit is same as the value of polynomial at that particular point x. And that's the definition of limit. So if limit x going to a, f of x is equals to f of a, then f is continuous at a. And for every polynomial, you will get this particular equality. So that's why every polynomial is continuous function.
By this definition, we can say like every polynomial is continuous.
That's the definition. Correct.
Okay.
We can say every polynomial is actually a continuous function. And that's why we uses this particular continuity to draw a polynomial. So that means for drawing a polynomial, we always say that if you join all the point with using the smooth hand, then that will be the graph of polynomial. So because of this continuity only.
Okay.
Okay. So now let's go to differentiability, which was the main topic.
Ma'am, I have one doubt, ma'am.
Yes.
Ma'am, if I have two functions in the factorization form, which is called f of x by g of x, I can compute them by limit through factorization. I will get some answer x, right, ma'am? If there are 0 by 0 like that. Ma'am,
Yeah, I mean,
then if I directly substitute x naught, which is called the name f of x naught by g of x naught, it goes to either of the value right now. I think
no. See, if you
those
have
are not
rational
equal.
function, that means quotient function, then if you have factor, then you can cancel it out. But if you don't have any factor which is common, then you have to decide by the power of p of x and q of x. So if the power is, I mean, so for example, this thing, that suppose limit x tending to 0 of x square upon x. So here one factor I can cancel out, which is x, but there will be another factor. So suppose x square is not here, x into x minus 1. If I take then, so here x can I cancel out and the limit will be minus 1. But in some cases it will cancel out, but the polynomial is some different. So you have to judge by looking the power of 1. Okay.
By substituting
So
the limit value
no,
also
no.
we can
Direct
factorize, no?
substitution will work only in this case if you don't have equal to 0. I mean q of x not equal to 0. In this case, substitution works. In this case, first you have to cancel out the factor and then do the substitution if the substitution makes sense. Okay. Is that clear? Or still you have a doubt?
Yeah, ma'am. My doubt is while substituting the x naught in those without limit, we can factorize those. That was my doubt, ma'am. Can we do like that?
Means I'm not getting.
Ma'am, while you computing through limit, we can factorize if there are factorize, we can factorize and cancel out the right, ma'am.
Right. And after that,
Ma'am,
we can substitute the value.
yeah, my doubt was when we don't go through limit, we can directly substitute the value in those function. Can we factorize then, right? Then, ma'am, that side.
I don't think that makes sense because if you just substitute the value, then it will be a real number. What you will factorize, right? If you
No, ma'am.
substitute the value, okay. So
I'm
we'll
not going
discuss.
through like that.
We'll discuss that later. So let's come to differentiability because first I have to cover differentiability and then we can discuss after this topic. Okay.
Yeah, okay.
So differentiability of a function at x is equals to a. As I say that differentiability is nothing, mathematically differentiability is nothing but a limit of certain quotient. So if you consider a quotient function, so suppose you consider a quotient in this fashion. So we want to discuss differentiability at point A. So if you consider a quotient f of a plus h minus f of a upon h, or this quotient that f of z minus f of x upon z minus x. Okay, in these two questions, if you apply the limit h going to 0, and here if you apply the limit z going to x, then these two limit if exist, then we say that if any one of them, because they are actually equal, I'll tell you how they are equal. So if any one of them are equal,
What is this
and if any
quotient?
one of them are, which quotient?
What is this quotient? How it is coming?
So it
F
is
of a
The
plus
concept
second
of
one,
h.
differentiability.
I'll tell you. Professor just uses this one, but what happens sometimes this is also very easy to handle, so that's why I'm introducing it so that you should know both of the quotient actually denote the differentiability of function, and I'll tell you how the second one comes just right after defining this. Okay, so if any one of them are exist, then we say f is differentiable at point x is equals to a. So this one is familiar to you, the uppermost. So here what you do, you just have to consider in place of h, we are considering the second variable z. So here what we do, so if you consider, so let z is equals to a plus h if you consider, then as h approaches to 0, this z approaches to a, right? So here you can also take a in place of x. Okay, so here what happens? So if you consider this limit, I'm just little bit modifying this particular limit so that it will be little easy to handle. Okay, so sometimes the second question is also easy to handle, and sometimes first question is easy to handle. But the differentiability can be defined via these two questions also. So if in future, if you see such type of differentiable, such type of question, then you should know that this is also one scenario where we can define differentiability using this. So how it actually comes from the first one? So what we do, we just use a little substitution. We substitute z is equals to a plus h. So that means in place of a plus h, I'm substituting z. So as h goes to 0, z also approaches to a. So what does it imply? So it implies that if you consider limit h going to 0, f of a plus h minus f of a by h, then this is same as limit as h goes to 0, then z goes to a. So that means z goes to a. In place of f of a plus h, what I have f of z. And this will be minus f of a. It will be as it is. And in the denominator, I have h. So what is h? So h is same as, if z is equals to a plus h, then h is same as z minus a. Right? So this is same as z minus a. So this is a little substitution. So if you will see this particular question, then also you have to understand, okay, this is nothing but a differentiability of a function only. Is that fine?
How the first quotient derived?
The first one?
Yes, yes.
Okay, so how this actually come into picture? So you want to know the motivation behind the definition of differentiability. Okay.
Yes.
That's the question, right? So what happens? So in geometric scenario, if you consider, so suppose you have any curve. So suppose this is your curve, and suppose you have any point P, right? And the coordinate of this particular point P is let's name it to be A and F of. And what we want to do, we want to actually judge the rate of what we can say, either the rate of change here, or we want to judge where our function is growing after this particular point. So my function is growing in this particular direction, right? In this direction, the function is actually growing. So what is our main purpose? So our purpose is to understand where our function grows after this particular point. So that means where is actually this function growing, in which direction? Either it's going upward, it's going downward, either it's increasing or decreasing, or where it's going. So at this particular instant, so here the main point is we want to know at this particular instant a comma f of, not any other neighboring. So what we do, so we modelize this scenario by saying that, okay, so we don't know at particular instant where it's growing, but we can say that if we reach from function, if we reach from point q, whose coordinate, let's take it to be e minus h, because this is a little left hand side of a, so it will be e minus h and f of e minus h, right? So what we can say, okay, we can consider this particular line and then apply the limiting criteria here. So if you apply the limiting criteria, that means if you tell your point q, just go and say hi to p. So that means how does that can happen? So we can use limit. So we can actually say that here, if we apply the limit h going to 0, because as h goes to 0, this a minus h will approach to a, and this point q will approach to point number p. So what we can say that, okay, so if whatever that particular limit will be, that will actually shows us where our function at this particular instant grows, right? So that's the main motivation. So here what we are doing, so we want to consider limit h going to 0 of which thing. So here the difference of two function we have to consider. So because this value is f of a and this value is f of a minus 1, sorry, f of a minus h. So that means the difference of these two things, that means f of a minus h, what is happening to this particular line segment as we go, h goes to 0. I mean, as this a minus h approaches to. So this is the quotient here. Okay, so the main thing is we want to judge the behavior or the increasing, decreasing nature, or the turn, or what we can say, where is our curve growing, in which direction our curve is actually growing. So what we do, we don't know at particular instant what is happening, but we can say if we take any point q, which is either the left hand side or right hand side of this particular point, and we tell this particular point to approach to p, then whatever the direction of this particular line, that direction will tell us the particular growing direction of our curve. Are you getting my point, what I want to say?
If it is positive, then it's in the upward, and it's negative, then it's going downwards.
Yeah, so this is one direction we are approaching p. We can also consider another point q dash that can approach p. So this, if you guys remember, then this is nothing but the left hand derivative, right? So this is the expression for left hand derivative. That's how we compute the left hand derivative. So ultimately we are using the limiting criteria itself. So I'll just repeat what I want to say. So the main purpose is to understand in which direction our curve or our graph or our function is going. Okay, so that's the main thing. So suppose I'm considering a very easy function. So this is our function. So I want to understand at this particular point, where is our function grows. So this function is actually growing in this particular direction. So suppose this is some line which is touches at this point and grows over this particular direction. So how we can just this particular scenario? That's the main purpose. So for that, what we do, okay, we don't know at this particular instance what is happening, but we can consider some points which is actually near to this particular point P, and then use our limiting criteria to judge the particular behavior. So suppose I'll take any point Q here. So then what can I say? So if you consider this line, which is actually joining P and Q, so this line will turn into this particular line if the point Q goes to the, if the point Q approaches to the point Q. Is that fact clear? How this line actually convert into this line, right? Because as Q moves from here to P, this line actually changes and become this particular line. So that's our main purpose, to judge what is the direction or what is the slope of this particular small line, right? The slope of this line. So here, if you consider the coordinate of P to be a comma f of a, and the coordinate of Q, since Q is actually a little left toward a, so that's why I'm considering a minus h. Here h is any positive number, so the coordinate of Q will be a minus h comma f of a minus h. Then how do we understand this particular behavior that Q is approaches to P? So we use the limit here. And what will be the limit? So limit is nothing but the difference of these two values. So here the value of function will be f of a minus h, and here the value is f of a. So what we do, we say that limit h goes to 0 of this particular quotient f of a minus h minus f of a by h will tell us where does our function goes. Because here what is happening, again I'll want to give a very precise thing for this quotient. So this quotient is nothing but the change in function value from this particular point to this point, right? So if you observe
Rate
very
of
closely,
change.
I think rate of change, you can say. So that's the thing we have to judge using differentiability. F of a minus f of h.
It's f of a plus h minus f of a.
If you want to consider a plus h, then you have to consider q here, q dash here, because then only it will be a plus h, right? So yeah, so
ideally h equal to 0, then what will be the result?
So we don't actually know what will be the thing at h is equals to 0. So that's why we want to compute the limit. Because at h is equals to 0, how can we say where is our curve growing? Because we just have one point there, right? So how can you say just by looking at this point where our curve is going? We know we want some information at least around very small neighborhood, right?
Okay.
Then only we can say, okay, started from here, then goes here, goes here, goes here. So that's the one thing we have to understand. That's why limit is very helpful if you want to see. This is a one physical problem. We want to construct a line which is actually touches a point P and tell us where our graph is growing. So how to tackle this point? We consider one point which is actually near to this point and try to force a limit over this particular Q to approach P. Then we get the differentiability. Is that fine?
Hello, ma'am.
It's fine.
Yes.
Ma'am, I got the thing in numerator, that is f a minus f of a minus h. That is we are considering a point which is near to P point, which is moving closer and closer, and we are applied limit. But why in denominator H is come?
So H is there, na? Because H is nothing but A minus H. The same thing. The difference in value of function and difference in this thing.
Okay.
So if you compute it, it will be H.
Okay. Thank you.
Okay. So it's just a motivation. If you want to know more about this concept, I will suggest go to Tom Apostle. I think, no, not Tom Apostle, the calculus of, what is this? Pearson publication calculus is there, na? Thomas calculus. He explained very nicely.
3 volumes of Thomas calculus contain entire calculus.
There in the description, you can just read it out. Or there are several videos on YouTube which actually very nicely using some visual tool, they will explain you what is actually differentiability. So there is one video, if I remember. Actually, I'm not remember. Just Google it. You will find so many nice video which actually uses some graphics to tell you this scenario, which I am writing in pen and paper. They'll actually use some graphics to demonstrate this particular thing. Okay. So for our purpose, we know that differentiability is nothing but a limit, and that limit is this one. So that limit is going to 0. F of a plus h minus f of a by h. So if this limit exists, we say f is differentiable at point x is equals to a. And whatever the value of limit will be, that limit is denoted by f dash of. And this is known to be the derivative of function. Derivative of function f at point x is equals to. So the definition of differentiability is clear to everyone?
Yes,
You can say no.
But I have one particular question comparing the continuous function, continuity and differentiability.
Yeah, I'll come to that. That every differentiable function is actually continuous function. So we can actually, you can easily prove this remark. So this remark says that.
So in that case, at all points an, the function f of a minus h, this function actually differential function should exist, right?
Which function?
Whatever the one you written, f of a minus h minus f of a by h.
Actually, your voice is not clear, so I'm not getting which function.
Okay, so the differentiality function you mentioned, you explained just a moment ago, right?
Modulus function or floor function?
No. This function only. Derivative.
This
one.
Derivative function.
Yeah, a plus h minus f of a by h. So, if it is
if function is differentiable, then you want to say that derivative will be continuous. Is that the thing?
Yeah, it should be continuous, right? The derivative should be continuous. In that scenario, for all points, it should be derivable, right? So for all point a of n, the derivative should be existing, right? So why we have to specify at x equal to, a equal to a not only?
So it is possible that the function is only differentiable at one point. No, actually, it's not possible at particular one point. There will be some interval of point where the function is differentiable, but it won't be the case that it is differentiable for every real number. So we define differentiability at particular point only. So as we define continuity at particular point only, and we say that a function is continuous in whole interval if it is continuous at every point. Similarly, differentiability is also defined at particular point, and then we say a function is differentiable over certain interval if it is differentiable over every point of the interval. Okay. So this is one remark, that if a function is continuous, so if f is differentiable at particular point x is equals to a, then it will imply f is continuous at x is equals to. The converse is not true, and the very basic example will be modulus of x. Yes.
And why for only certain points?
Because see, we first define pointwise any property. I mean, these all properties are pointwise property. That means you are defining this property over some point. And then for interval, we say that if every point, if we have this particular property, then f will have the whole. Why pointwise? Because it makes sense to define pointwise, right? So as we use the sequences, so an can converge to a single point a only, right? So here also there is one significant of point. So you can say that since the definition revolve around point, and it's very hard to define, because what are intervals? So intervals are nothing but the collection of points. So ultimately, if you want to define something on interval, you have to define that particular thing over every point, right? It makes sense now. If something is collection of points, then it's better to define on one single point and then generalize it to that if this part differentiability is happen to all point in the interval, then it's differentiable interval. Is that fine? Convincing?
Okay. For just small chunks, it's defined, and for the other, it's
The large
generalized.
thing we can define just by saying that, okay, if it holds for everything, then the property holds. That's it.
Good question. So this remark is clear, but then you made a statement saying that the reverse is not true, right? If it's a
The reverse is not true.
And that is the case of mod of x, is what you said.
Modulus function. Right.
Can you just explain that mod of x is continuous, but it is not differentiable?
Yeah. So I'll give the. So suppose you have a function, modulus of function, right? Modulus of x. F of x is equals to modulus of x. So the remark is that this function is continuous at particular point 0. I am saying that at x is equals to 0, but not differentiable at x is equals to 0. Okay. So now there are two ways to prove this thing. So first is general ways, just by computing the limit and left-hand derivative, right-hand derivative. And the second thing is observing the graph. So I'll explain by the graph at the end, because I want to cover some more thing for that. So let's try to see how this is happening. First, we'll prove the continuity of f of x at x is equals to 0. So for continuity, what we want left-hand limit, right-hand limit, both should be equal. That means limit should exist and it's equal to the value of function. So what is this f of x? So f of x means modulus of x, which is equal to x when x is greater than or equal to 0, minus x when x is less than or equal to 0. So what will be the left-hand limit at x is equals to 0? So left-hand limit means limit extending to 0 minus f of x. But if we approach x is equals to 0 from the left-hand side, we are actually considering minus x behavior, right? So this is same as limit x going to 0 minus of x. And since we just observe that limit x going to any point x naught of this particular function, x will become the value. So it's equal to minus of 0, but minus of 0 is same as 0. So that means the left-hand limit at x is equals to 0 is nothing but 0. Similarly, we calculate the right-hand limit at x is equals to 0. So it will be equal to this limit x going to. Okay. So it will be equal to limit x going to 0 plus f of x. And here, if we approach x is equals to 0 from the right-hand side, we are using the description of x. That means as x goes to 0 plus, this is actually equal to x only. And this is equal to 0. So here what is happening? The right-hand limit is same as left-hand limit. And we know that the value of f of 0 is also 0. So that's why, because of these two things, we can say that limit x goes to 0, f of x exists and it's equal to 0, which is same as the function value at 0. So that's why the function f of x is equals to modulus of x is continuous at 0. Is that
Correct.
fine? Continuity at 0?
Yeah. Till this, I understood.
Now for differentiability, we will use the left-hand derivative and right-hand derivative concept. So I haven't defined it. So what is the left-hand derivative? So left-hand derivative is nothing but the left-hand limit of this particular quotient. F of a plus h minus f of a by h. Okay, so you can actually convert this particular 0 minus limit into some limit which actually says that h goes to 0. So if h goes to 0 minus, so that means h is less than or equal to 0, strictly less than 0. So what you can say that h goes to 0 minus is same as h goes to 0, but in place of h, we just replace h by minus h. Okay, because if, okay, so I have to start over because, so here what is happening? So the limit involves h goes to 0 minus. So that means h goes to 0 minus means we are approaching 0 from the left hand side of 0, right? So this particular thing is same as by saying that h goes to 0, minus of h goes to 0 for any h belong to real number. Is that fine? These two things are same.
Yeah,
Because
that's right.
if you say h goes to 0 minus, that means we are approaching 0 from left hand side. It's same as saying minus h goes to 0 for any h belongs to real number. So what is my main aim here? To remove this particular minus thing, because it's a little complicated if I want to check right hand limit, left hand limit description, right? So what I do, I'll convert this particular limit into some limit which we can easily handle. So it's same as, and again, minus h goes to 0 means h goes to 0. Right, these all two things are equal. So we can say that this particular limit is same as limit h going to 0 f of, now in place of h, I'll replace minus h. So here what I am doing, in place of h, replace minus h. Okay, so it's f of a minus h minus of f of a upon minus of h. And this is the thing we always compute for left hand derivative. Same as limit h going to 0. Just little modify. So f of a minus f of a minus h upon h. So this is the left hand derivative. And similarly, we can compute the right hand derivative also. So what will be the right hand derivative? The right hand limit of that particular quotient. And again, if you do the same procedure, you will get limit h going to 0, f of a plus h minus f of a by h. Okay, fine. So these are the two, left hand derivative and right hand derivative you have to compute. And now what I want to say for differentiability. So differentiability means the limit of that particular quotient should exist. And we know that when will be the limit exist? If the left hand limit and right hand limit is same. And what is the left hand limit of this particular quotient? Is same as left hand derivative. So this is the left hand limit of quotient. What is the quotient, you guys know? And this will be right hand limit of the quotient.
So left hand limit or a derivative? Derivative and limit are two different things.
Two different things, because what is happening here, we are actually doing a little bit modification in left hand limit and reaching toward this particular expression. That's why it's known to be left hand derivative. Not
Correct, correct. You have written left hand limit of the quotient. That's why I asked that. What you are saying is right, not a limit of the quotient.
I mean, it comes from the left hand limit of quotient. That's the thing.
Okay, okay.
We consider left hand limit, do a little bit adjustment there, and come to this particular limit, right? So that's why this left hand limit is coming from the left hand derivative is coming from the left hand limit. So what I want to say, since in the differentiability definition, we want that limit to be exist, and the limit will exist if left hand limit is same as right hand limit. But here, in place of left hand limit, what we have? Left hand derivative. So that's why the differentiability definition give us a condition that if left hand derivative is equal to right hand derivative, then obviously at some point at a, at x is equals to a, then function f is differentiable at a. Is differentiable at a. So I just want to give a little explanation for this particular remark, that why it is true that when left hand derivative and right hand derivative are equal, we actually says that our function is differentiable at that particular point. And this is true because we are just using the same same definition as we use this for limit, that if left hand limit, right hand limit equal, that means limit exists, and limit exists means same thing as here for differentiability. Is that fine?
Yes, yes, this is fine. Yeah, I'll take a deeper look into it. But yeah, thank you for explaining this.
So this is the thing. Now we can use this particular description for proving that modulus of x is not differentiable at x is equals to 0. Okay. So what we do? So let's compute left hand derivative at 0. So left hand derivative will be limit x going to 0. F of a will be 0, and minus f of a minus h. So f of a minus h means 0 minus h upon h. right? So this is same as limit h going to 0, f of 0 minus f of minus h by h. Okay, so now here what is happening? When we have minus description here, matlab minus of x we have, then we know that modulus of minus h will become plus h. So this is same as limit h goes to 0. Here we will be, here it will be 0 minus of modulus of minus h upon h. So limit h goes to 0. And we know that modulus of minus of h is nothing but h. So it will be minus h upon h, which is equal to minus. Correct? H and h will get cancelled out, minus will be. Now what happens if we have the right hand derivative? So right hand derivative will be limit h goes to 0, f of a plus h minus f of a by h. This is actually equal to limit h goes to 0. Here we have 0 in place of a. So it will become modulus of h minus 0 by h, which is equal to limit h goes to 0. Modulus of h will become h only, so h by h, and the right hand derivative is equal to 1. So here left hand derivative not equal to right hand derivative, which will imply that modulus of x is not differentiable at 0. Is that fine?
But it is continuous, no?
But it is continuous at 0. That's why this remark holds in only one direction, not the other. So you can say that if you construct the set of continuous function and differentiable function, then this is, if you consider the Venn diagram, so suppose this is your universal set, then this will be the Venn diagram. So here the smaller one will be all those function which is differentiable, right? So this is the differentiable function, and this the bigger circle is actually continuous function. So that means if a function is differentiable, then we can say that it will be continuous at that point, but the converse is not. Okay. Is that fine?
Yeah, this is good. Thank you.
So now I just, yes. Any doubt so far?
Nope.
Okay, so now let's go to the rules of differentiability. So there are 3 rules, product rule, quotient rule, and chain rule. So I want to describe them, and then we will talk about linear approximation. Okay, so what are the product rules? So you guys, I think, are familiar. So this f dash of x is also written in this form, that d by dx of f of x. These two descriptions are same, and they actually denote the derivative of f, the derivative of f at x. Okay. So now we have 2 rules. So one is the product rule. So product rule says that if you have 2 functions, if you have product of 2 functions f of x and g of x, then their derivative, that means d by dx of these 2 functions, is nothing but first function, second function's derivative d by dx of g of x, and plus second function, first function's derivative d by dx of f of x. And if you are interested to prove this particular thing, then you can use left hand derivative, right hand derivative description. Apply that here, and you will find out left hand side and right hand side are actually equal. Okay. So I left the proof for yourself. Just try to do it. It's very easy. Just have to use left hand derivative, right hand derivative concept for proving it. Okay. Or just use the limit only. Don't bother about left and right hand derivative. Just use the limit which we discuss for differentiability. You'll get your answer. Okay. Now the second one is the quotient rule. So the quotient rule says that the derivative of a quotient of 2 function f of x and g of x is actually equal to this particular quantity. So this is g of x the whole square, g of x d by dx of f of x minus of f of x d by dx of g of x. Okay, so these 2 rules are there, product rule and quotient rule. And the third one is the chain rule. And the chain rule says if you have composite function, then you can actually use the derivative of 2 function to compute the derivative of composite function. So that means the derivative of d by dx of f composite g of x, this is also same as d by dx of f of g of x. So this is actually equal to take the derivative of first function at the point g of x and then take the derivative of second function. So This is d by dx of f of g of x. So now here, this will be a point into g dash of x. Okay, so that's the chain rule. Now let's try to solve. I think you guys are familiar with the derivative of some simple function. That means the simple rules that d by dx of x to the power n is equal to n x to the power n minus 1, and d by dx of e to the power x is equal to e to the power x, and all those things, right? Derivative of sine function is cos function, derivative of cos function is minus sine function. And we can actually compute all those things using our definition of limit also, but since we don't have time now, so that's why I'm not doing that. Is that
Ma'am,
fine
once
so far?
explain that before function which you have written, like derivative of f of g of x.
So if you have composition of two function and then you want to compute the derivative, then what you will do, you will compute the derivative of first function and substitute the point g of x as it is, and then compute the derivative of second function. So suppose let's take one example here. So suppose you want to compute the derivative of f of x is equals to e to the power x to the power n. So suppose you have this function e to the power x to the power n. Let's take it to be square here for precise value. Then if you want to compute the derivative of this function, what you will do? So first you will define two functions whose composition is this particular function. So if we consider f of x to be equal to f1 of x to be equal to e to the power x, and f2 of x to be equal to x square, then you observe that f of x is nothing but the composition of these two functions, correct? Then f of x is nothing but first we are using e to the power x. First we are squaring x and then applying e. So that means it's f1 of f2 of x, right? If you calculate it, so that means f1 of f2 of x, and this is same as f1 of f2 of x is what? f2 of x is x square. Now what is f1 of x? f1 of x is e to the power x. That means it is e to the power x square. So that's why this function f of x is nothing but the composition of two functions. Now here, if you want to compute the derivative, you have to use chain rule. So then f dash of x or d by dx of f of x is actually equal to, first what you will do, you will take f dash of f1 dash of f2 of x into f2 dash of x. Okay. So now what is f1 dash of x? So if f1 of x is e to the power x, this will imply f1 dash of x is nothing but e to the power x. And here f2 dash of x is nothing but 2x, correct? We just uses the basic formulas. So here f1 dash of f2 of x you have to do. So that means you have to take e to the power 2x, because e to the power x is, so that means f1 dash of what is f2 of x? That is x square. Sorry, not 2x, x square. So here f2 dash of x will become 2x. So now f1 dash of x square is nothing but e to the power x square. So this is e to the power x square into 2x. So this will be your answer, 2x e to the power x. That's how you have to apply repeatedly the chain rule.
Yeah, thank you.
Is that fine?
Yeah, yes.
So these three are very basic rule for differentiability, and I hope you guys know the basic differentiable function. That means derivative of sine is cos and all those things. We don't require much higher formulas, just the basic formulas up to trigonometric, tan function, sec function, cosec function, and all this. And the log function also. So we need them. Now, one topic is left, that's the linear approximation of a function. So let's try to cover it.
Ma'am, tangents before that.
Yeah, tangents also, no? So tangents and those two things are. So let's go to tangent first. So what is a tangent? So tangent is the line which actually tell us where our graph is growing. So in the previous thing, that one line we are discussing, that this particular small line, this line is actually the tangent, and the slope of tangent is given by the derivative of function. So because what does the differentiability tell us? Differentiability tell us in which direction we are actually growing, our curve is growing in which direction. So that direction is calculated by derivative of function. So, and whatever that particular line is known to be the tangent of function at that particular point. So, what is tangent? So, a line L which tell us the direction of growth of function, growth of f at point x is equals to a is known to be a tangent. Okay, and here is one thing that you can also say that a tangent is nothing but a line which touches the graph exactly at one point, but that's another description. So if a function is differentiable at this particular point, so if f is differentiable at x is equals to a, then the tangent is the line which passes through this point, which passes through point a comma f of a with the slope f dash of a. Okay, so if your function is differentiable at x is equals to a point, then the tangent line is actually a line which passes through the point x comma f of a, a comma f of a with the slope f dash of a. Is that fine? Okay.
Yes, ma'am. Yes, ma'am.
And there is one equivalent condition for differentiability also, that if you are able to find one unique tangent, then you can actually say that your function is differentiable at that particular point. So if there exists a unique tangent, at point x is equals to a, then f is differentiable at x is equals to a. Okay, so this is one equivalence condition. For proving this, we need a little bit of work. So you can take it as a remark you can consider. If you are able to draw a unique tangent, then function will be differentiable at that particular point. So we actually use this thing to observe the graph and tell at which point the function is not differentiable. So this is the thing we need if you want to say that modulus of x is not differentiable at x is equals to 0. This is actually the definition only, the tangent definition. And this is one remark you can say, and this is the second remark you can say. So I'll repeat. So what is a tangent line? So tangent line is nothing but a line at a point which actually tell us about the direction of growth of our function, or in which direction our curve is growing. Okay. So we connect the description of tangent with differentiability, because we know that differentiability also tell us the same thing. So what we say that if a function is differentiable at particular point A, the tangent is nothing but a line passes through point A comma f of A with the slope f dash of A. Because f dash of A is the differential quotient, whatever we computed. And we know that this quotient also tell us the same thing, where our graph or our curves grow at that particular point A comma f of A. And then we have one remark, and this remark says that if we are able to draw a unique tangent, then we can say that our function is differentiable at x is equals to a. So we can use this remark to tell which are, by looking the graph, we can actually tell at which point our function is not differentiable. So for example, if you consider the graph of f of x is equals to e to the power, modulus of x, then what is happening? So this is the graph. So this is the graph. So at x is equals to a, we can actually draw several tangents, because tangent is nothing but a line which passes through curve, which touches the curve exactly at one point. So if you draw this line, then this is also a tangent. This line, suppose it's not cutting it. So suppose this is the line. So this is also a tangent. So here we can draw several tangents. So that means this particular function is not differentiable at x is equals to 0. Is that fine?
Yes, ma'am. We have proved it in
Ma'am,
this limit thing.
okay.
Yes, Manish.
Ma'am, could you comment on x power 1 by 3, ma'am? Graph of
X power, So x power 1 by 3's graph look like this. It also has a sharp corner in this. Something
no,
like
ma'am.
this.
It will come from down, right, ma'am? Negative y-axis.
Oh, okay. Something like this. It looked like it's a smooth curve, but what happened? If you try to draw a tangent here, that's also not possible because function is not differentiable here. So even though it looked like smooth, but if you compute the left hand and right hand derivative, they are not equal. Am I right? In case of x to the no x to the power
Yes,
1 by
in
3
zero
is
cube
Actually,
root
what
is
happens
asking.
is, ma'am, like in the lecture, from week 2, if we draw the conclusion of tan of 90 degrees is not possible, right? Like it's undefined. So
right. Same
for
situation
vertical
happens.
tangents, the graph is like a bit more, it will go stretch more to vertical, and then it'll take a right turn. It doesn't take a steep right turn. So
Right.
yeah.
Correct.
So
that's
I am not
also
able to understand why it is like 50-50. I've understood. Yeah, some sort of. I'm not able to
okay.
like, process it.
So see, if you compute it via the limit, then it's very clear that y is not differentiable, right? Because the left hand limit is not equal to right hand. So if you consider x to the power f of x to be equal to x to the power 1 by 3, then I think sir already computed that left hand derivative not equal to right hand derivative at x is equals to 0. Am I right?
I also don't. I guess it is limit is possible. I guess. Why not?
Let's compute it.
Yeah, please.
Ma'am,
Because it's a continuous
at the zero, here it will more flattened.
I think the right hand limit or something is coming to be 1 by 0 type. Let's compute it. So what will be the left hand derivative? So left hand derivative limit is going to 0. So it will be f of a. So here I am considering at x is equals to 0. Right. So f of a will be 0 minus of f of e minus h. That means f of minus h by h. So it will be limit h going to 0. So it is the cube root of minus h upon h. So this will be equal to minus of limit h goes to 0. So this will be h to the power 1 by 3. Cube root of minus h is well defined. H to the power minus 3 upon h. So it will become limit h goes to 0. 1 upon h to the power 1, 1 minus 1 by 3 if you do, it will become 2 by 3 here. And minus of this is 1. So again, we know that as h goes to 0, this will be undefined quantity, right? It will be come to be minus infinity type. You are agree with this? Similarly,
yes,
right hand derivatives also, if you compute, it will become h to the power 1 by 3 upon h, which is again 1 upon h to the power 2 by 3. Right? So it is limit h goes to 0. It is 1 upon h to the power 2 by 3. And this also goes to infinity as h goes to 0. So here, left hand derivative and right hand derivative are not equal. Right? Not equal. And not equal, they are not giving us a finite quantity. So the situation, so by the left hand derivative, right hand derivative, we can easily say that f of x is not differentiable at x is equals to 0. Is that fine so far? Manish?
Okay, I just made
Derivative
an
does not exist, right? So when it is infinity or minus infinity, we can say that the derivative does not exist.
Derivative does not exist. Correct.
as per the observations that we have seen so far, that for the sharp turns we don't have derivatives defined. In this one, it is a curve, so we can't just trust on the figure we see. We have to
Figure to see that. Do this arithmetic here, but see this cube root of x3 has a very what we can say saddle point. In the future lecture, you guys know about the saddle point thing. So what is happening here? The graph is actually increasing, but around 0, some portion will be there where this is where which it is neither increasing nor decreasing type of thing. And then
just
it
going
will
along with the
go
axis.
something.
Yes, ma'am. It will
So
go along the
some
y-axis a
Not
bit
with the
high.
x-axis.
So something like this type of scenario happens. So that means here around 0, the function is neither increasing nor decreasing kind of thing. I mean, such kind of
Ma'am,
behavior happens. So that's
it
another
is
reason.
more, yeah, ma'am. Actually, it is more flattened.
Uh-huh.
According to the y-axis. No, y-axis. So
According to
at
the
y it
y-axis.
is, yeah.
Yes, ma'am. It
Yeah,
will
yeah,
stretch
yes.
more
It is
above
Correct,
y-axis.
correct.
So where we
Right.
can't find any tangent, so that we can say it is not
This
differentiable
is not
because
differentiable. Because
because tan
cubic
90
is this type,
yeah,
so
yeah.
that's why
He was
it will
telling
be
right.
something.
Elango sir is telling right. Tan 90
Right,
it's not defined. So can
It's
we?
not defined.
Yeah.
That's
that
why
is the
also we
reason.
cannot define a tangent here.
Yes.
So yes.
Ma'am, I'm having a small question regarding limit. I was watching a revision lecture. So x square plus 1 for x greater than or equal to 0 and x cube plus 1 for x less than or equal to 0 is the function of f for which limit is calculated.
What is this? The last
Yes,
one?
ma'am. X cube plus 1.
Okay.
X cube plus 1. I feel the limit is not existing because just beside the 0, right side to the 0, it is positive value, and just before the 0, it is negative value.
No. That's not the case. Because what? Yes, you're right that if you consider any point which is the right side of the 0, it will be positive, left side it will be negative. But as you approach to 0, the value of a function will approach to 1, because here if you compute the left hand limit, so the left hand limit will be limit x going to 0 minus of f of x. So from the left hand side, we are taking this particular polynomial, the cubic polynomial. But we know that as limit x goes to 0 minus, if you consider this expression x cube plus 1, this actually goes to 1 only, right? We want that value where our function approaches.
Now I get it. Now I understood. So indirectly we substitute 0 only, right?
Indirectly we substitute 0 because of the polynomial nature.
Yes, ma'am.
Okay. So one thing is left. So that will be the equation.
Based on the above question, it is limit is there, but it is not differentiable, right?
I think it is differentiable.
Means at x equal to 0, we have different. It is 2x and 3x square. So we are getting two different.
No. Just try to compute it. I am not sure, but as I observe it, I think it will be differentiable. Just try to compute it, the derivative, you will get your answer.
Ma'am, linear
I'm not sure,
approximation
but
is left, no?
Linear approximation. That's why I want to state the equation of tangent and then we go
Tangent
to
and linear approximation.
But that's also okay. See, derivative of differentiability of this thing, you can one shortcut I can say that. So suppose any piecewise function is given to you, it's greater than or equal to 0. This is x cubed plus 1. No, x less than 0. So what you can do, left hand derivative will be derivative of this particular right hand derivative will be derivative of this uppermost function. So here the right hand derivative will be look like 2x, and as x goes to 0, this 2x also goes to 0. This is a one shortcut trick. If you understand, that's also fine, and not, then that's also fine. So left hand derivative we compute using this expression. We know that this expression is differentiable. So left hand derivative will look like something like this: 3x square plus 1. And this goes, 3x square only, not plus 1. Plus 1 will become 0, right? So this also goes to 0 as x goes to 0. So that means left hand derivative, right hand derivative will be equal to 0 as x goes to 0. It will be equal to 0 at x is equal to 0. At x is equal to 0. So in my mind, it's a differential function. But just go through the description and try to observe. Is it differential function? This trick you actually can use for polynomial functions. If you have a piecewise function, just observe what will be the left hand derivative, what will be the right hand derivative, then conclude it at particular point. Okay. Good. So now let's go to the equation of tangent. Or else we can start it by today. Today also we have open session, so we'll cover these two topics in that session. If it is fine for you guys.
Small. Tomorrow will you only be the sorry, my bad. You will be only sorry. Will you be taking the session only tomorrow, like, or someone else?
Tomorrow's session, I think someone else will take because I have other sessions. So
okay.
I won't be able to. But I'll tell them that we left
Okay, ma'am. No
two
issues.
topics. Because linear
Thank you.
approximation takes time. I want to explain a little bit about it.
Yes, ma'am. Thank you so much, ma'am.
If you guys have any doubt, I'll be here for 5 minutes more. So we can discuss.
Oh, then I'm having a small doubt, ma'am.
Yes.
There is a sequence 3 plus 5 plus 7 till 2n minus 1 divided by n square. Find the limit, ma'am. I am having confusion in that.
So
because,
this is also the sum of n odd terms, right?
No, we can't say that, right, ma'am. 1 is not here, right? 1 plus 3, if we substitute, like if we did you get it? N square, we can't take it n square.
So just add plus and minus 1.
Yeah.
No, then n value will be like
basically the count is n squared minus 1, right?
1 minus 1 upon n square. Then we can change this expression with n square minus 1 or n square. What is this? The sum of first
n square, n square.
This is n square. Total it is n square minus 1.
N square minus 1 upon n square. So it will be equal to 1 minus 1 by n square. So the limit will be 1. So
okay. Okay. Yes, so now I get it. Yes, ma'am. That's the right answer. Okay.
Anything else from anyone?
This is called finding the limit x tends to 0 log base in 1 plus x by x.
X tending to 0 log
base. Yeah, 1 plus by x.
1 plus? Your voice is not clear. X by?
X, I put in the chat.
Okay, fine. Limit x going to 0 log of 1 plus x by x. Now this by x is in log or outside of the log? I mean, is this the case? So here you have to use L'Hospital rule. Okay, I haven't covered the L'Hospital rule also. So yeah, 3 topics available. So here you have to use L'Hospital rule because as x goes to 0, this log of 1 plus this goes to minus infinity, I guess, right? Because this is the log function, we are adding 1 step, so it goes here. So as x goes to 0, it goes to minus infinity. So you have to do some adjustment and apply the L'Hospital rule. So x goes to 0. X goes to 0. So
yes,
this also goes to 0.
1 by 1
this
plus
goes
x.
to minus infinity.
Substituting x equal to 0. Yeah, L'Hospital we can do. It's a general
sorry. Right. 0 by 0.
1. Yes, ma'am.
Because of this one.
It's a general case.
General case. So just apply L'Hospital rule. So if you apply L'Hospital rule, we have to differentiate. So it will become 1 plus x upon 1. So this will be equal to 1 upon 1 plus x. And we know that this goes to 1 as x goes to 0. So that's your answer. So yeah, L'Hospital rule also I have to come. I'll share this PDF over the calendar. So there I'll upload one link. You can access this PDF using the link. And please bear my handwriting because I don't think it's
Ma'am, I'm having a derivative function. Like I want to find the differential d by dx of that function. Once could you?
Okay.
Yeah. 1 by 2x.
Okay.
Whole to the power of x. Yeah,
This
d
one?
by dx of this. Yes, ma'am.
So here you use chain rule. So assume this is your first function f1. This is your, the whole power is your second function f2. So what you'll know, for this type of function, we have to use log and then apply the derivative. Because this is x to the power x type of case. So here what you do, so suppose this is your f of x. So then apply the log first. So that means log of f of x. is the log of 1 by 2 to the power x. And now use the property of log. Bring this x over here. Log of 1 by 2 to the power x. Sorry, 1 by 2x. And now apply the product rule here. So now dy dx of here you will get composition of two functions f of x, right? Here if you apply the product rule, it will become log of 1 by 2x plus x as it is. The log will be, what is the derivative of log? Log x is 1 by x, right? So it will become 2x into, we have to do the differentiation of this also because chain rule, right? One log differentiation, one the innermost function differentiation. So it will become minus 1 upon 2x square. Okay. So now
one step backside. Yeah. Minus 1 by 2x. After the till product, I understood, ma'am.
So here you have to use the product, right? So this side also we have to use chain rule. So I'll do that later. So here first I differentiate x. So derivative of x will become 1. This function will stay as it is. Then x will stay as it is. I have to do differentiation of this function. Log of dy dx of log of 1 by 2x, right? So now this is one composite function. So first I will do the derivative of log. So derivative of log is 1 by x, correct? So but here in place of x, we have 1 upon 2x. So the derivative of log will give us 1 upon 1 by 2x into, now we have to differentiate 1 by 2x also. So the derivative of 1 by 2x will give us minus 1 by 2x square. Is that fine now?
Yes, ma'am. Yes, ma'am.
Chain rule just.
This is the right answer, right? Ma'am, I have done, there is a formula, right? A power x d by dx is equal to a power x of ln a. Do you remember?
But this is not a, right? I also think that it's a composition of these two functions. It's something else. I mean, if you consider this thing that suppose our function f1 of x is equals to e to the power x, then what you will consider the f2 to make these two composition equal to something like this, e to the power x to the power x. That's the reason. So here this is something like x to the power x. In place of x, we have 1 upon 2x. So this is 1 by 2x is here. And then if you composite these two functions, f1 composite f2 of x, then you will get 1 by 2x to the whole power x. But again, you have to do differentiation of x to the power x. So this differentiation, we don't have any formula. So here you have to use this log trick.
Yeah, okay, ma'am. Understood. Thank you, ma'am.
Ma'am, I have sent you some screenshot in the chat box.
Yeah, got it. So what's the doubt here?
Just open it.
Yeah, ma'am, a quick question before we move on to this problem solving. The session that we are talking about tomorrow is at the same time, right? Where you said that you will say that these two topics have not been covered.
Yeah.
Same time,
it's
right?
actually on the same time.
In this question, which I have sent you, in the line m equal to log x base equal to a to the power m equal to a, and the second line, they're finding out b. But from the above three equation, how can they are writing b to the power mr? It should be nr, na?
B to the power r is equals to a. So we want to compute x in terms of p, m, and r. So b to the power r to the power m should be there. Because if you observe the last equation, first equation, then x is equals to e to the power m. So in place of a, if you substitute b to the power r, then it will be b to the power r to the power m is equals to x. So here they have missed. R should be before and m should be last. Are you getting what I want to say?
But x, how can it be x equal to something? I'm not getting that.
Screen visible now?
Yes, your screen is visible.
Here, see, this thing is there. So this means x is equals to e to the power m. But what is here a? So a is equals to b to the power r. So if you combine these two, x is equals to b to the power r to the power, right? So it is x is equals to b to the power r and b. Same thing. But here they miss r and we should switch. Or maybe there is another way in which we can get this. Is that okay now?
Now got it.
The substitute in place of that. Okay. So yeah, that's all for today. If you guys have any doubt except problem solving, then we can discuss it for 5 minutes.
Ma'am, one small
Otherwise,
doubt. On a rough
yes.
view, like you will be given some kind of graphs, like how we can distinguish, like at which graph, like it is differentiable or not differentiable. I just want to know about it.
So see, there will be at most 2 or 3 criteria. So first thing is the graph will be discontinuous. Discontinuous graph is very easy to find, right? There will be some gap. So first thing
Yeah,
is
yeah.
that gap. Second thing is this corner point. So if the corner point is there, then also the function is not differentiable. And the third thing is if graph is finishing at that point. Finishing means there is nothing. It will be the end point of type of thing. So if a graph stop at particular point, then it will be not differentiable type of. So 3 things only can happen if graph is given to you and observation of differentiability.
Okay, ma'am. Thank you.
Okay.
Yeah,
I'll upload this. Yes.
Sorry, this is not something to do with the subject. This is something
Mhm.
because I doubt whether I'll be able to take the final exam this time. So in this case, if I'm going to not take the final exam, and if I take, I don't want to take, for example, next, obviously I won't be clearing the subjects in this case. So for the next semester, instead of math and math, if I take, can I take some other subject and complete math the following semester? Because I want to take, I want to take both the maths consecutively. That's one plan because 1 and 2 I want to take continuously. And but for that, I find that I need some kind of program skills. I felt like maybe I can do with Python and then come back to math if I couldn't take the final exam this semester.
Actually, I actually don't have any idea about this. But one thing you can do, you can ask Vishal sir about this thing.
Okay.
He will take a Tuesday session maybe.
Okay.
Because I haven't gone through the process, so actually I don't know. But if in this meeting, if you have, I mean, if someone knows this answer, then you guys can talk.
Ma'am, I have sent you a symbol. Please define the symbol, what it means. F of
It
xn.
means not implies.
Oh, f of xn, the symbol f of a. Means f of xn not implies f of a.
Yeah, I mean, this uses for statements. If you have one statement and the another statement, तो उन दोनों statement को combine करने के लिए you can imply not imply वाला symbol. Yes, Sridhar, you can ask someone else or you can ask to Vishal sir. He will be the right person to guide.
Sridhar, आपका doubt क्या है?
No, the thing is, I doubt whether I'll be able to, for some other engagement, I doubt whether I'll be able to take the final exam.
Yes, you will take the final exam if you're.
I won't be able to take the final exam because I have something coming on the day, on that week. To be frank, next month I have some other thing popping out. So if I couldn't take the final exam, obviously I won't clear the subject. So whatever the subject I have taken this semester, but I want to take math. My plan was to complete math 1 and then continue with math 2, which is also mandatory in this thing, in a consecutive manner. But if I couldn't complete this semester, I just want to know whether I can skip math next semester and take some other subject, like for example Python.
You are unable to totally attend the entire semester.
If you're not able to, if somebody doesn't have a final exam, then it's a 0. That's it. There is no mark for it.
It's
That's
a
how
0.
it is being treated.
Final exam is the main thing.
Even if your final exam is the main criteria.
Yes,
because
main
even if you
criteria.
attend Q1 and Q2, final exam is the main criteria. So even if you get sent in Q1 and Q2 also, if you don't attend final exam, then you are not.
You have to repeat again from the January
repeat
term.
the whole thing. So my idea is to just, in this case, I want to take max continue in the consecutive semester. Actually take the final exam. The plan is to continue with my Python, and then I want to do math in the next semester.
Have you completed your graduation?
Which graduation?
college graduation, 3 years bachelor degree.
Yeah, of course.
Yes, you have already completed your graduation.
Yes.
Then you can take direct diploma entry.
No. For some reasons, I just want to start from scratch. So that's also the case.
You don't
No.
need
That time when I didn't know, because my diploma that time I didn't know about this thing, so I just applied for this. Later I got a call from that. I said like you can continue with the foundation from the foundation.
No, you don't need to take the.
Fine. It's fine. It doesn't matter.
Hmm.
So I just want to know that. Fine. I will talk to Vishal and I will clarify.
How we can connect with Vishal?
He will come for the next Tuesday. He will be there.
Yeah, he is also one of the instructor.
Okay.
Okay, I think we are tracking the time now.
So, ma'am, hello.
Thank you, Samiksha.
Ma'am,
thank you
thanks a
guys for
lot
joining.
for a wonderful session. Your explanations and
Thank you so much.
approaching towards the
Thank
questions are very much good. I hope you will
Okay,
take
so
more
one
sessions
thing,
in future.
Ma'am,
yeah,
you
graph
are
theory
getting
obviously
fans.
I'll take.
Yes,
Right.
yes.
So
Yes,
one thing
Ilango.
is, can you guys go and check the calendar link? Is it working or not? That PDF I have uploaded just.
Just wait a minute.
Week-8
Yeah, it's
summer
working.
session.
It's working.
Okay. Fine. Thank you guys for joining.
Yes, sir.
Thank
Yes,
you.
sir.
Thank you so much, ma'am.
Thank you so much, ma'am.
Thanks.